The geological timescale is a system of chronological measurement that relates stratigraphy to time, and is used by geologists, paleontologists, and other Earth scientists to describe the timing and relationships between events that have occurred throughout Earth's history. The table of geologic time spans presented here agrees with the nomenclature, dates and standard color codes set forth by the International Commission on Stratigraphy. Evidence from radiometric dating indicates that Earth is about 4.54 billion years old. The geology or deep time of Earth's past has been organized into various units according to events which took place in each period. Different spans of time on the GTS are usually delimited by changes in the composition of strata which correspond to them, indicating major geological or paleontological events, such as mass extinctions. For example, the boundary between the Cretaceous period and the Paleogene period is defined by the Cretaceous-Paleogene extinction event, which marked the demise of the non-avian dinosaurs and many other groups of life. Older time spans which predate the reliable fossil record are defined by the absolute age terminology. The largest defined unit of time is the superaeon, composed of eons. Eons are divided into eras, which are in turn divided into periods, epochs and ages. The terms eon, utham, eratham, system, series, and stage are used to refer to the layers of rock that correspond to these periods of geologic time in Earth's history. Geologists qualify these units as early, mid, and late when referring to time, and lower, middle, and upper when referring to the corresponding rocks. For example, the Lower Jurassic series in chronostratigraphy corresponds to the Early Jurassic epoch in geochronology. The adjectives are capitalized when the subdivision is formally recognized, and lowercase when not, thus Early Miocene, but Early Jurassic. Geologic units from the same time but different parts of the world often look different and contain different fossils, so the same period was historically given different names in different locales. For example, in North America the Lower Cambrian is called the Wauchoban series that is then subdivided into zones based on succession of trilobites. In East Asia and Siberia, the same unit is split into Alexian, Attribution, and Bothamian stages. A key aspect of the work of the International Commission on Stratigraphy is to reconcile this conflicting terminology and define universal horizons that can be used around the world. Anthropocene. The term Anthropocene is used informally by popular culture and a growing number of scientists to describe the current epoch in which we are living. The term was coined by Paul Crutzen and Eugene Stoimer in 2000 to describe the current time, in which humans have had an enormous impact on the environment, polluting its oceans, killing its species, etc. It has evolved to describe an epoch, starting sometime in the past and on the whole defined by our carbon emissions and our plastic that is left in the ground. Opponents of this term say that the term should not be used because it is very hard, if not nearly impossible, to define a specific time when humans started influencing the rock strata, defining the start of an epoch. Others say that humans have not even started to leave their biggest impact on Earth, and therefore the Anthropocene hasn't even started yet. Whatever the case, the ICS has not officially approved the term, as of September 2015. History and nomenclature of the time scale. Early history in ancient Greece. Aristotle saw that fossils of seashells from rocks were similar to those found on the beach and inferred that the fossils were once part of living animals. He reasoned that the positions of land and sea had changed over long periods of time. Leonardo da Vinci concurred with Aristotle's view that fossils were the remains of ancient life. The 11th century Persian geologist Avicenna and the 13th century Dominican bishop Albertus Magnus extended Aristotle's explanation into a theory of a petrifying fluid. Avicenna also first proposed one of the principles underlying geologic time scales, the law of superposition of strata, while discussing the origins of mountains in the Book of Healing in 1027. The Chinese naturalist Shen Kuo also recognized the concept of deep time formation of primary principles. The principles underlying geologic time scales were later laid down by Nicolas Steno in the late 17th century. Steno argued that rock layers are laid down in succession, and that each represents a slice of time. He also formulated the law of superposition, which states that any given stratum is probably older than those above it and younger than those below it. While Steno's principles were simple, applying them to real rocks proved complex. Over the course of the 18th century, geologists realized that sequences of strata were often eroded, distorted, tilted, or even inverted after deposition. Strata laid down at the same time in different areas could have entirely different appearances. The strata of any given area represented only part of Earth's long history. The Neptunist theories popular at this time proposed that all rocks had precipitated out of a single enormous flood. A major shift in thinking came when James Hutton presented his theory of the Earth, or an investigation of the laws observable in the composition, dissolution, and restoration of land upon the globe before the Royal Society of Edinburgh in March and April 1785. It has been said that, as things appear from the perspective of the 20th century, James Hutton in those readings became the founder of modern geology. Hutton proposed that the interior of Earth was hot, and that this heat was the engine which drove the creation of new rock. Land was eroded by air and water and deposited as layers in the sea. Heat then consolidated the sediment into stone, and uplifted it into new lands. This theory was called Plutonist, in contrast to the Neptunist, flood-oriented theory. Formation of geologic timescale. The first serious attempts to formulate a geological timescale that could be applied anywhere on Earth were made in the late 18th century. The most influential of those early attempts divided the rocks of Earth's crust into four types: primary, secondary, tertiary, and quaternary. Each type of rock, according to the theory, formed during a specific period in Earth history. It was thus possible to speak of a tertiary period, as well as of tertiary rocks. Indeed, tertiary and quaternary remained in use as names of geological periods well into the 20th century. The identification of strata by the fossils they contained, pioneered by William Smith, Georges Cuvier, Jean de Marius d'Orloy, and Alexandre Brogniart in the early 19th century, enabled geologists to divide Earth history more precisely. It also enabled them to correlate strata across national boundaries. If two strata contained the same fossils, chances were good that they had been laid down at the same time. Detailed studies between 1820 and 1850 of the strata and fossils of Europe produced the sequence of geological periods still used today. Naming of geologic periods, eras and epochs. The process was dominated by British geologists, and the names of the periods reflect that dominance. The Cambrian, and the Ordovician, and Silurian, named after ancient Welsh tribes, were periods defined using stratigraphic sequences from Wales. The Devonian was named for the English county of Devon, and the name of Carboniferous was simply an adaptation of the coal measures, the Old British geologists' term for the same set of strata. The Permian was named after Perm, Russia, because it was defined using strata in that region by Scottish geologist Roderick Murchison. However, some periods were defined by geologists from other countries. The Triassic was named in 1834 by a German geologist Friedrich von Alberti from the three distinct layers, red beds, capped by chalk, followed by black shales, that are found throughout Germany and northwest Europe, called the Trias. The Jurassic was named by a French geologist Alexandre Brogniart for the extensive marine limestone exposures of the Jura Mountains. The Cretaceous, as a separate period, was first defined by Belgian geologist Jean de Marius d'Orloy in 1822, using strata in the Paris Basin and named for the extensive beds of chalk. British geologists were also responsible for the grouping of periods into eras and the subdivision of the Tertiary and Quaternary periods into epochs. In 1841, John Phillips published the first global geological timescale based on the types of fossils found in each era. Phillips' scale helped standardize the use of terms like Paleozoic, which he extended to cover a larger period than it had in previous usage, and Mesozoic, which he invented, dating of timescales when William Smith and Sir Charles Lyell first recognized that rock strata represented successive time periods. Time scales could be estimated only very imprecisely, since various kinds of rates of change used in estimation were highly variable. While creationists had been proposing dates of around 6,000 or 7,000 years for the age of Earth based on the Bible, early geologists were suggesting millions of years for geologic periods, with some even suggesting a virtually infinite age for Earth. Geologists and paleontologists constructed the geologic table based on the relative positions of different strata and fossils, and estimated the time scales based on studying rates of various kinds of weathering, erosion, sedimentation, and lithification, until the discovery of radioactivity in 1896 and the development of its geological applications through radiometric dating during the first half of the 20th century, which allowed for more precise absolute dating of rocks. The ages of various rock strata and the age of Earth were the subject of considerable debate. The first geologic timescale that included absolute dates was published in 1913 by the British geologist Arthur Holmes. He greatly furthered the newly created discipline of geochronology and published the world-renowned book The Age of the Earth, in which he estimated Earth's age to be at least 1.6 billion years. In 1977, the Global Commission on Stratigraphy started an effort to define global references known as GSSP for geologic periods and faunal stages. The Commission's most recent work is described in the 2004 Geologic Timescale of Gradstein al. A UML model for how the timescale is structured, relating it to the GSSP, is also available. Condensed graphical timelines. The following four timelines show the geologic timescale. The first shows the entire time from the formation of the Earth to the present, but this compresses the most recent eon. Therefore, the second scale shows the most recent eon with an expanded scale. The second scale compresses the most recent era, so the most recent era is expanded in the third scale. Since the Quaternary is a very short period with short epochs, it is further expanded in the fourth scale. The second, third, and fourth timelines are therefore each subsections of their preceding timeline as indicated by asterisks. The Holocene is too small to be shown clearly on the third timeline on the right, another reason for expanding the fourth scale. The Pleistocene epoch. Q stands for the Quaternary period. Millions of years table of geologic time. The following table summarizes the major events and characteristics of the periods of time making up the geologic time scale. As with the time scales above, this time scale is based on the International Commission on Stratigraphy. This table is arranged with the most recent geologic periods at the top, and the most ancient at the bottom. The height of each table entry does not correspond to the duration of each subdivision of time. The content of the table is based on the current official geologic time scale of the International Commission on Stratigraphy, with the epoch names altered to the early, late format from lower, upper as recommended by the ICS when dealing with chronostratigraphy, a service providing a resource description framework. Web ontology language representation of the time scale is available through the Commission for the Management and Application of Geoscience Information. Geoscience project is a service under SPARQL endpoint. Proposed Precambrian timeline. The ICS's Geologic Timescale 2012 book, which includes the new approved timescale, also displays a proposal to substantially revise the Precambrian timescale to reflect important events such as the formation of the Earth or the Great Oxidation Event, among others, while at the same time maintaining most of the previous chronostratigraphic nomenclature for the pertinent time span. Hadeanian 4600-4030, Maya Chaoshan era 4600-4404, Maya, the name alluding both to the mythological chaos and the chaotic phase of planet formation. Jack Hill's Ian Orza Conian era 4404-4030, Maya. Both names allude to the Jack Hill's greenstone belt, which provided the oldest mineral grains on Earth. Zircons. Archean Neon 4030-2420, Maya Paleo-Archean era 4030-3490, Maya Akistan period 4030-3810, Maya, named after the Akastan Ice-Sijuan period 3810-3490, Maya, named after the ISUA Greenstone Belt Mesoarchean era 3490-2780, Maya Volbaran period 3490-3020, Maya, a portmanteau based on the names of the Kapval and Pilbara Cratins Pongolan period 3020-2780, Maya, named after the Pongola supergroup Neo-Archean era 2780-2420, Maya Methanian period 2780-2630, Maya, named for the inferred predominance of methanotrophic prokaryote Siderean period 2630-2420, Maya, named for the voluminous banded iron formations formed within its duration. Proterozoic Eon 2420-541, Maya Paleoproterozoic era 2420-1780, Maya Oxygen Ion period 2420-2250, Maya, named for displaying the first evidence for a global oxidizing atmosphere Jatulian or Eukaryon period 2250-2060, Maya. Names are respectively for the low Magundi Jatuli Delta 13C isotopic excursion event spanning its duration, and for the first fossil appearance of eukaryotes Columbian period 2060-1780, Maya, named after the supercontinent Columbia Mesoproterozoic era 1780-850, Maya Rodinian period 1780-850, Maya, named after the supercontinent Rodinia. Stable environment Neoproterozoic era 850-541, Maya Cryogenin period 850-635, Maya, named for the occurrence of several glaciations Ediacaran, period 635-541, Maya, shown to scale. Compare with the current official 1.